Okay, yeah, thanks. Okay, so hello everyone. Welcome to the week 8 of the problem solving session for the course on computational complexity. And the topics for today would be more on circuits, and we'll look at some other. So last time we saw these complexity classes, NC, um, yeah, NC0, NC1, and so on. And then we also saw the AC complexity class. Okay, and there are several classes that are there above this and below this. So currently the picture that we have is we know that NC0 is contained in AC0. This is contained in NC1. Sorry, yeah, AC1, and so on. So this is an infinite hierarchy that we have. But there are things that are inside this and there are things that are outside this. So you can think of so the basis for this was and or negation gates, and okay, and you can think of defining the basis as something else. So instead of the and or gates, let's say I'm giving you threshold gates. So instead of the and or functions, you are computing a threshold of k inputs here, and so on. So actually you can define it to be anything. You can define it to be any function that you would want, but and you can define your own class based on that. So yeah, so just to give a sense that this is not the only landscape that we have. There are things above and below. Okay, but we'll not get into it. And yeah, okay. So um, what we also discussed last time was this class called p/poly. Okay, I'll define this when we get to the questions of that kind, and we also show that this is same as p size, which is the set of all functions that have their exister poly-sized circuit computing f. Okay, so we'll see some questions on this. So we'll define it soon. Okay, so let's start our discussion from maybe where we left off. So okay, so we say that a function f is symmetric if its value depends only on the Hamming bit. So that is, it only depends on the number of ones that are there in the vector. That so you can think of these x1 to xn as the inputs, and no matter how you permute it. So for example, f of x1 to x1, x2, x3 is same as f of x2, x1, x3. This is same as f of x2, x3, x1, and so on, for any possible arrangement that you can imagine. If the value of the function does not depend on the order of the inputs, but only on the total number of ones in it, then you say that it's a symmetric function. So this is the definition of the symmetric function, and this is one definition and this is an equivalent definition. You want to show that both are the same.
Yes. So the summation. So G is acting as a transformation function here, but then the argument of the function G is a summation of all the xi's. And if it is a normal summation kind of the thing, then this the values of, so basically we are computing that whether this sum is an even quantity. What is the sum? What is the sum? Say if the sum came out to be say 100, then what would be the meaning of the G of the 100 thing? So, but then this G is taking, n number of the arguments. But from where do we get the n number of the arguments? Because this summation will return a single value, isn't it?
Yeah. So okay. So okay. So maybe we can write this better. So mm, hmm. Or maybe think of it at this as the same way, but the weight of uh, G is only going to be one of these. uh, I mean, G could be either 0, 1, 2, and so on up to n. So exactly one of these is going to be a 1. So if the weight is 2, the corresponding value would be 1, but everything else would become a 0. So we can think of this as a Boolean function over n variables, where if the ith variable is 1, then we know that the weight of the function is.
So weight of the function is equal to the value of argument. So I need to look into the one value here and say if the one value came out to be corresponding to the input, say 100. So then that would mean that the weight of the function is 100, and but then this
No,
g will always.
no, you are right. So this should not be 0 to n. This should be 0, 1 to the n. I mean, this is a very, I mean, you can write it better. Actually, you only need 0, 1 to the log n, because the maximum weight that G could take is n. You only need uh, log n bits to represent that. So this is actually how it should be, but we can also think of it as over n bits.
Yes, that's true, but I'm unable to think that how this g is transforming the value. I mean, I need to have, so in the right hand side, I mean, when can we have the value of the g of anything equals to a 0?
Mm, are you talking about these values?
Yes, yes. So which argument should I pass to this g function so that g returns a value 0?
So that depends on f. Hmm.
Uh,
Okay,
but
so it should be such that it respects whatever f was.
Oh, I see. But then when can we have the value of f even is equal to 0? Because what I think that this f function is a symmetric function, and that only depends on the Hamming weights, and Hamming weights is equal to the number of ones in the string.
Hmm. Hmm.
So irrespective of whichever permutation I apply, because whatever permutation I'm going to
Hmm.
apply, this will keep the
Hmm.
number of ones intact.
Hmm.
So that is fine, but
Hmm.
when do we get the value of even this Boolean function is equal to a 0?
So that is given to you by this function. So because you're given f, you have a truth table of f. So you have x1 to xn and the value, that the output value of it. So let's say on all zeros, say f outputs a 1. Maybe if there is exactly one number, I mean total number of ones is 1, then maybe it says 0. Okay. So this f that is given to you has I mean is basically like a truth table where you know the value on every possible input.
Yes, I understood this thing that in whatever order I assign the values to the Boolean literals x1 to xn,
Hmm.
if the number of the ones remains the same, I mean
Hmm.
throughout the assignment,
Hmm.
quite possible that in one assignment I may assign value 0 to x1, and in another assignment I assign the value 1 to the x1. But then if the number of the ones in the Boolean literals are same, so then function is going to return the same value.
Hmm.
And if that is the case, and then we are looking for that instead of taking, so we can take the summation of, I mean, the sum of all these variables, and I apply a function g on it.
Hmm.
So, but then what's the meaning of taking the sum of the Boolean literals? Would it be an OR operation, or would it be what kind of the operation? So how will you write this x of I? Because if you take the normal summation, like if you treat this, I mean the values as 0 or 1, so that is going to return a numerical value only.
Hmm.
And then what could be the meaning of the g of a numerical value? How can the g of, or the transformation of a numerical value would came out to be a 0 or a 1? Like what is the value of g of 99 and what is the value of the g of the 100? How can this happen that g of the 99 is equal to a 0 and the g of 100 is equal to a 1? So I am having doubt in interpreting the summation of xi's.
Okay. So got okay. So um, okay. So let's say for now that I'm okay. We know that the summation of xi's can take a value between 0 to n. Hmm. So what we'll do is I need only log n variables to represent any number between 0 to n. So think of these as an ordered tuple. So x1, x3 up to xn, these are ordered tuple. When x1 is 0, when all are 0, this represents that this is the decimal value. Okay, so if I write 0001, then this represents the decimal 1. If I write 0010, this represents the decimal 2, and so on. So when I write all ones, this will be 2 to the, this will be n minus 1. Okay, so I might need one more bit to represent n. So I'll probably end with 1 and all zeros. That would be n for us. But yeah, so um, so think of the summation that we are getting, which is an integer. Think of it as a write it as a binary representation and think of that as input to G.
Oh, yes, it makes sense now. So now, since we are representing that the decimal number as a binary, and their corresponding Boolean literals will become either 0 or a 1.
Hmm.
So now that, so the thing is that, yes, so yes, so then there is a Boolean formula and whose value, and I need to keep the f intact. So if f is resulting into a 1, so this g should also result into a 1. So that would mean that if I represent 100 as a Boolean, as a binary string, and I apply f function on it, then that would be same as uh, the binary equivalent of the 100. So in this case, don't we have say f and g both as the same functions? Like say, so in the left hand side, basically you are representing 100 in terms of the binary, and in the right hand side you are applying a g function over the binary equivalent of the value 100. So both f and g are the same functions, are the same functions. It only says, if this interpretation, I understood this thing correctly, it only says that the function of a binary is equal to another function applied over the, so function of a binary is equal to another transformation applied over the binary equivalent of a decimal. Nothing more than that.
Um, I mean that would be one way to see that, but yeah, but yeah, the main point is just that it's a very it's a very special kind of function where, so for example, if I give you a function over n bits, any Boolean function, we may not always, be able to write it as a function over smaller number of bits.
Why so? Why so? Because and why so? I mean, in this entire question, what is not? The fact that the function is symmetric has not been used. I mean, we have not used the idea of the Hamming weight here, because had this been a non-symmetric function also, then also probably this equality will hold true if I go by this interpretation.
No. So, okay. So, let's say that the function is not symmetric. So, in particular, if here, um, I mean, in the second row also, the sum of the the number of ones is still 1, but the output is 0. Here also the number of ones is 1, but the output is 1. So this is not a symmetric function.
Yes, yes, I
Okay,
understood.
so
Yes, yes.
Okay, so basically, why this sort of a reduction is happening is because um, we are, I mean, saying that a lot of information about f is redundant, that it doesn't really matter whether xi is 1 or xn is 1. All that matters is just a small amount of information about the sum of the input bits.
Yes.
That's why
Yes.
we could reduce it to a smaller function.
Yes.
Okay,
Yes. And
so
so how can this be equals to the g of the summation of xi z? So
hmm,
as if so indirectly the question probably the question is asking that in whatever order you assign x1
hmm,
the values to the x1 to xn,
hmm,
you just need to bother about their summation and nothing
hmm.
more than that.
Yes, yes.
Yes. So, but then how to prove this? That
Hmm,
there would always exist such a function g, and
hmm,
that would treat I mean these arguments
hmm,
merely as their summations and nothing more. Their order is not mattering, not does not matter here.
hmm,
Only their summation matters.
hmm,
So how to find this g is not clear there.
hmm. Okay, so can we think of something like an induction?
So I can think of I mean induction like say if I only take n is equal to 1, so then f of x1 is equal to the g of x1. This is fine. The g appears to be same as f. I mean I can do some other transformation like say if I pass the value of x1 is equal to 1, then the f of x1 is also returning 1 and the g of x1 would also return 1. So as if I am taking this OR with a value say 0. Doesn't matter whether I take its OR with a 0 or 1. So this f and g both could be an maybe realizing this OR function.
Hmm.
If I take say, so I assume that this is true for x1 till xa, and I am
Hmm.
able to get the same thing. But if I add one more variable here,
Okay,
then
I think.
that is key.
Are you trying to come up with a circuit for G? Is that
Yes, yes, yes.
okay?
Because without
So
circuitry, I mean, how would I show that? Uh,
okay, so one thing we know is that if you give me a function in the form of a truth table, for example, or any representation, then you can always come up with a circuit for it. That is
right.
something we know, right? Uh,
Yes.
yes. So in this question, it's not because we didn't say anything about the size of the circuit for G or the depth of circuit for G. So it's not necessary that we should come up with an explicit circuit. If we could show that it's just a function of the summation of the variables, then that would be enough.
Um, okay.
Okay,
Uh,
right. I mean, are you convinced that, I mean, just showing that there's a function G is enough?
yes. 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 Uh, yes. Uh, so yeah. So f of x1, x2, and x3
Hmm.
would be same as the g of the value 3, assuming that x1 is 1, x2 is 1, and then x3 is 1. So instead of taking all the values as 1, let us take say two values as 1 and 1 as 0. So then f of x1, comma x2, comma x3 should be same as the g of 2.
Hmm.
And
Hmm.
if any two values are
Hmm.
a
Hmm.
are 1.
Right.
So if I have a very complicated expression in the left hand side, complicated Boolean expression in the left hand side, so with two number of the ones, the possible I mean in how many ways can I form
Hmm.
the Boolean formulas? So out of so first position could be say in two ways, the second could be in two. So there would be four such functions wherein I would be having exact two ones. I mean out of the eight possibilities. No, there would be
There would
seven.
be
No, there would be seven. No,
three.
there would be four. There would be four such formulas in which I have exact two ones. So therefore, we do not discriminate in between these three. We should find a g function such that whether I pass f of 1 1 comma 0, the g of 2 should return. I mean the outcome of all the three functions should be equals to the g of 2. and we have to find one such G function that preserves this thing. So what would that function be? So if f of 1 1 comma 0 is returning a 1, but then in all the three cases the g of 2 is fixed. So if g of 2 is fixed, so what that function be? And that is what this question has become very interesting actually. So if yeah, but then the function is symmetric. So since the function is symmetric, so in whatever order I permutate them, I'm going to get the same result. So if I'm going to get the same result, like say here in the first function, say whether you write say, so basically these are the permutations. These are the permutations. Are these no? But then with the three values, 110. In how many different ways can I permutate these values? Three, three to six permutations are possible. So if six permutations are possible with the three values, and I have to ensure that say.
Okay, wait. What do you mean? Six permutations with the three values as in?
So because say if I consider the arguments at x1, x2, and x3, so how many permutations are possible? Say one is 1, 2, 3, 2,
Right,
3, 1. In that sense, so total
yeah.
six possibilities are there.
True.
So since the six permutations are possible, and but then I have to ensure that out of these six permutations there should exist two ones. So then, how many such permutations are possible? Because, but it's okay. I would be having six permutations only. So out of these six possibilities, I mean, all these six functions should evaluate to the same thing, and that is the g of
Okay.
that is g of two. So now we have to find what that g function
Okay.
is.
1 second. Okay, so let's say, okay, I'll write it in terms of, okay. So you're saying that f of x1, x2, x3, um, okay, but okay, for you, the g of 2 means that the summation of xi is equal to 2.
Yes,
Yeah,
yes.
so x1 plus x2 plus x3 is equal to 2. So we should only focus on those those values where this is satisfied. So how many such substitutions can there be where x1 plus x2 plus x3 is equal to 2 is satisfied? So those would be only 3.
Uh, but then would be three, maybe three, because I cannot think of any other possibility. Like say the other could be 0, 1, 1, but that has already been included. So we have three here, but then we can have six permutations, isn't it? But then out of those six permutations, with x1, x2, and x3, there could be six permutations. So why do we have only three values?
Bec-
Uh,
huh.
yeah.
Because not all of them would satisfy. Um, um, I mean, some of them would actually turn out to be equivalent because when the moment you say that x.
Yes. Right. Yes. So many will become equivalent, and now, but then this is again an interesting problem of permutation combination. Okay, because if some values are same, then how many different combinations are possible? So okay, but then the value came out to be three. And now the thing is that these three values should return, I mean, should evaluate to the same as the g of two. That is what we need to prove. And so what that GB and which is unaffected by the ordering of the X1, X2, and X3. Uh, but then since we know these values, so what can be done if I take some end kind of a thing or some, so in what way should I apply this thing? So, I mean, can you think of this parity kind of a thing? If something can be done with parity thing stuff. So, like, say, if I compute this addition here and say this is system of two, um, or not sure. Yeah.
But again, are you trying to construct the G as a circuit or do you just want a function?
So, like in this case, I'm just looking for a function in the sense that function is so very liberal kind of a thing, as you said, that their order, I mean, in the Boolean function, the ordering of the variables, do not matter. The only thing matters is the count of the ones.
Hmm.
So, how many of them are one?
Hmm.
And if the count, if the number of the ones is same, then we are going to get the same result. And we have to show that what that function is. That only depends on the number of the ones and not their order.
Right, right. So, okay. So that means, okay, we want to show that, yeah, f of x1 to xn can be written as uh, a function that depends only on the sum. Okay. So I think you're trying along the correct line. So I'll just I'll just give some direction. Um, so to show this, we can think of an induction on the sum of uh, xi. So this can take values between 0 to n.
Yes.
Okay. So naturally the base case would be that say the summation, I'll call this k. Okay, let's say that the sum is 0. Then in that case, how can that happen? That can only happen if all the variables take a value of 0. There is only one case.
Yes.
Okay, so in that case, let's say f of all zeros, let's say that's the value that it computes, because you are given f as a truth table. So x1 to xn, when all are zeros, let's say the value that it took was f0. So this could be some 0 or 1, depends on what was given to us. I'll call it um, okay, let me call it b0. F sort of gives a feeling that it's a function, whereas it's only a bit, so I'll call it b0.
Yes.
Okay. So base case is done because I'll set my g to be such that whenever the sum that is given to me is 0, I'll output b0.
Right.
Okay, so this is done. Now uh, let's say that I knew that whenever the sum of the variables is, okay, k is a bad notation now. Okay, I'll remove that, summation xi. Okay, so by hypothesis, let's assume that whenever the summation of xi is equal to k, then f can be written as a g which um, depends only on the summation. Okay, okay. Now, what you want to show is that, let's say that the summation of xi is equal to k plus 1. Okay, now I'm not even sure whether we need induction, but okay, let's go ahead with this. Okay, then what changes now? So like how do we go about it?
So there could be two possibilities for the additional xi. It could either be a 0 or it could either be a 1. So if I include a 0, and that is not going to alter the summation, and probably that will not alter the value of the function f as well, because the value of f, whatever is the value of f, is for x1 till xn, and if I add a 0 also, since it will not change the number of the ones, it is not going to change the value of the function f either. So, and the second possibility could be that I add a 1 here. So, if I add a 1 here, so then it will change the value of the function. but then basically we were looking for that what is the g of the 1 in that case. I mean additional earlier whatever the value of g was for the summation of xi's for I varies from 1 to n, and now we are adding a additional value, say x of n plus 1 here.
Hmm.
So what will be the behavior of the function g there? Quite possible that so I mean if additional x n plus 1 is 0, then no
Uh,
impact.
but okay, I mean, we don't have one more additional variable because the variables that are given to us are already fixed, x1 to xn. What could happen, however, is that some variable xi that was here, which was earlier 0, now becomes a 1.
Then in that case, you could have used say inductive induction over say n minus one, and then might have tried to show it for n xi is equal to n instead of proving it for say summation of xi is equal to k plus one. You could have
Hmm.
we can try to show for summation of xi is equal to k, and hypothesis would be that the summation of xi is equal to k minus one is true. So. So in that case, say it is true for the f of x1 till xn minus 1, and that equals to the g of the summation of xi's, and wherein I vary from say 1 to n minus 1. And now we will show that this is true for the summation of uh, xi is equal to n is equal to k in this case. I mean,
Okay,
in the
so
inductive hypothesis, you could have written say
so
summation of xi is equal to k.
you want to assume for k minus 1 and
Yes.
proof for k. Uh, but I mean, these are the same. Uh, I mean, these are the same things. No, assuming for k and showing for k plus 1 is equivalent to.
Yeah, this is okay, but then since you said that the number of the inputs are fixed are equals to n, I mean the number of the Boolean literals are fixed, say from x1 till xn.
Hmm.
Because for me, since we are using mathematical induction here, so these x1 density till xn are these are mere integers and nothing more than that. Uh,
Hmm.
so since these are integers only, so it is okay if I prove it for k plus one, and then for the plus one element, I told two possibilities. Either it could be a zero or it could be a one. If it is zero, then this induction works because then there won't be any change in the value, neither in the value of f nor in the value of g. However, if uh, uh, if the plus one is a one, then
Hmm.
we'll have to think that f may result into a one or may result into a zero. Then what would happen to the function g?
I think the same problem would arise here also.
So I said this thing. It's true. The same problem will arise here also. But then this was in response to your suggestion that we have only k number of the. I mean only n number of the Boolean literals. Actually, we do not have n plus one number of the Boolean literals in
Huh.
that sense.
So,
Otherwise, the applicability is same in both of these.
hmm. Only that k here ranges up to n minus 1.
Right. Yes. So, but then, I mean, even I'm not sure that are we applying mathematical induction in the right way here,
Yeah, I
because
think, yeah, in order to only show that G exists, we don't really need induction. We can directly do that, but probably for constructing a circuit for G, this might be useful. Like we did in the last lecture, assuming by hypothesis, we assumed that there is a circuit for up to um, we had removed one variable there and we had a smaller subcircuit. We had some gh there and yeah that I mean, so probably we'll need this step only for the construction of the circuit, but for showing the existence of g we don't. That is very, I mean, induction would be very strong tool. Yeah.
yes. Yes.
Yeah.
So,
So yeah. Hmm. Um. Okay. Okay. So basically, I mean, the proof of this would um, just be that, okay, let's look at the case where summation of xi is equal to k, and mm, and we will look at all possible ways in which um, the summation of xi can be k. So it could be that the first k variables are k, the rest are 0, and so on. So how many such possibilities are there? This is uh, okay. So
this would be
in
NCK in, I mean, we can place here.
exactly, this is n choose. Okay. Huh. Okay. So this is n choose k, and you have these many uh, ways in which we can have uh, that the summation is k. But by definition of the symmetric function, we know that all of them must compute the same value.
Yes.
Yes, and yeah, and in each of the cases, observe that the summation of xi is equal to k. I mean, that's how we started our case. Okay, so hmm, okay, so hmm, so at this point we can say that the summation of xi depends only on the sum of the number of ones in, or the sum of the inputs. So yeah, so um, yeah, so showing that the existence of, I mean, showing that g exists only requires this simple observation. I think that should be enough.
Uh, it's okay, but then what that G function is? What kind of, I mean, so is there any example of such a G function, like say identity function, or and similar, something similar to that? What that G
What
function?
the g function is depends entirely on what the f function is,
Uh,
because
yes.
because the f could say that when the sum is k, then I should output a 0, so that will tell, okay, that at this particular point g should output a 0. For example, let's take a symmetric function which is let's say or function, or okay, maybe or would be very simple. Let's take parity function. hmm. Okay, so let's say suppose f is a parity function, then what does g look like?
Yes. So if f is a parity function, so then okay, so we can write say even like say if the number of the ones is even, then let us say the value of f is a zero, and if uh, we have odd parity, and then let us say that the function f is the value is a one. So
hmm.
then what we can do that, so if we have even parity, so the sum would also came out to be even. So then I can define this g function as a mod 2 function. So yes, and so if I define this g as a mod 2 function, basically g would be an XOR kind of thing.
Exactly.
So yes, so from the
So
f we could find it. Yes,
so
that's true.
g in this case is just an XOR function, but
Right,
if
right.
huh, okay. Okay, so we saw two kinds of functions so far. So one is the symmetric functions. Okay, I'll just to put it into perspective. Um, so there are two kinds of restrictions that we can think of. One is the restriction on circuits, and the other is restrictions on the functions. Okay, so on the circuits side, we said that we have this, you can restrict the depth, fan in, or the types of gates that are allowed, you can restrict the size, and so on. These are the parameters. And some classical circuits that we study based on that are AC, NC, and
So what will be the depth of NC0? Constant. I mean log
log
raised to the power
to
0.
0, which would be constant, right?
Yes, yes.
Okay, and we also saw what are called monotone circuits, where you are only allowed OR and gates, no negation gates. And then we saw some restrictions on functions. One is the symmetric function that we saw just now, and the other is the monotone function. Mm, okay, and last time we saw that these are equivalent. That is, for every monotone function, there is a monotone circuit, and if you have a monotone circuit, then it must necessarily compute a monotone function. So this is something that we know. Okay, now okay. hmm. Hmm. Okay, so uh, yeah, so the thing is, we are looking at two parallels. One is where the circuits are being restricted, the other is where the functions are being restricted. And okay, okay, so okay, I did you ask something? Sorry, I forgot. Was there a question?
No, no, no. I mean, I got the clarity on this.
Yeah,
So I was asking about that. Does it exist such a G function? And then we could. I
right,
mean, yeah, that was a Montel function, right?
right. Okay, so hmm, okay. So okay, although we know one result like this, so symmetric functions could actually be non-monotone. So for example, um, we saw parity function. Let's ask this. So there can there be functions that are symmetric and monotone, functions that are symmetric, but okay, I'll just think of it as columns. Okay, can there be functions that are symmetric and monotone, symmetric but not monotone, not symmetric but monotone, and not both? So can we think of examples? Uh,
So I forgot. I mean, yeah, I mean, in the previous session, it was a long example. So monotone would stand say if x1 is less than x2, then f of x1 is less than f of x2 kind of thing.
yes, yes, correct. So, um, yeah, so think of this as a truth table, and we have all these values here, and whenever we look at any two rows, let's say this x and this y. Okay, y was a bad. Okay, x and x prime. These are two substitutions of x1 to xn. And okay, then we said that if x is less than equal to x prime, then if this is 1, this cannot become a 0.
Yes,
And
and yeah, and we counted. I mean, how did we computed this x is less than or equals to x prime
x
bit by
prime,
bit
bit by
or
bit, exactly. Yes, this is
bit
a
by bit from
bitwise.
right to left or from left to right?
So at every position, we want that uh, this is less than equal to the ith bit of this. So for all I in n, we want that xi is less than equal to xi prime. So the order does not matter, because you want this to hold everywhere.
Yes, yes. Now I understood. Yeah, I can recall now. Yeah. So,
Okay.
Yes. So now that if a function is symmetric, so then only the number of ones matters, and if the only the number of the ones matters, so will it be a monotonic? Uh, will it
Huh.
be a monotonic? So
Okay. So,
not necessary, not necessary.
hmm, not necessary. Correct. So, not every symmetric function is monotone. Question is, can there be a symmetric function which is also monotone?
Oh, okay. So if I am, so is this possible? Okay. So yes, so can there be a symmetric function and which is monotone as well?
Hmm.
All right. So I can do one thing, that I devise a function like this. The entire input is divided into say two halves.
Hmm.
So in the right half I have only ones. I have only ones. So I'm least bothered about the values of the whether the values are ones or the zeros in that half in the other string.
Okay, so
Right?
I'll
So
just
this,
draw that. Okay, 1 second.
yes.
So this is your truth table, and you're saying we will divide it into half.
Half, yes. So if I divide this into the half, so in the right portion I write all the ones. So I'm least worried about this one. And now I'm only worried about the values in the left hand side. Not like this, probably I mean to say that x1 say till xn, so x1 till xn minus 2, and then say from xn minus 2, n by 2, n by 2 I mean to say, x of n by 2, and divide and conquer kind of a thing, x of n by 2, and then x of n by 2 plus 1, and say till n. And I fix, so we are looking for such a function. So if I fix, can there be functions wherein so the function is symmetric, only depends on the value of the ones, and is monotone as well. So, but it is not necessary. But can there be a function? You mean to say? So if that is the case, then it should not matter whether I flip. Even if I flip the values
Hmm.
in the, then also there should not be any impact, and it should only depend on the number of the ones, and there should not be any impact. That whether I, so what if I have all the zeros in, so I unable to think, but
Hmm.
uh, so
All the
in such a
zeros
function,
meaning
yeah,
all the
yeah,
zeros here, or
all the zeros as the function values.
right? Yeah, that is correct. So yeah, so no matter what the input is, the function is a constant zero function. That's what you're saying.
Yes,
Hmm.
yes. So
So
if
this
this is
is,
the case, yeah,
yeah. So this is symmetric because I mean it does not depend on the order. It will always output zero. So it is symmetric, and it's also monotone because in any, if you look at any two x and x prime, uh, it never happened that from a 1 you went to 0 because you were always 0. So the constant 1 function is one example. Even uh, constant 0 function that you said is also an example. So this is this is true. So there can be, this is one example we saw is the constant 0 function.
yes. And for the second one, a function is symmetric, need not to be monotone.
Hmm.
Monotone, yes, it is true, and we can think of many examples.
Hmm.
But then, what that example be, and what that specific example be?
Hmm.
So clearly, if we go for I mean, alternating function, like say if I have the
Parity.
value of one kind of a thing,
For
so that would
example,
be symmetric, but then not monotonic.
for example, the parity function that you mentioned earlier, it is symmetric, but it's not monotone because
Yes. Yes.
okay. So
And for the third one, a function which is not symmetric, so it depends on the values of the ones. And then
hmm.
can this be monotonic? So can this be monotonic would mean that the number of ones is not dependent, but then monotonic would mean that I mean that inequality holds true. for all the values of I. So
Hmm.
whenever I find this thing, and I mean there should not be any change.
Hmm.
Uh, the value of the function should not be uh, less than that. So how is and the number of the ones is not preserved. So a function which is not symmetric. So we can think of any monotone function and which is not symmetric, and this thing will hold true. If a function is monotone, it need not to be a symmetric function.
Right,
So
right. So, yeah, so but I mean, if you have to construct one example, um, one explicit function like that, let's say like over three variables. Okay, so, um, okay, so,
so yeah.
hmm,
Yes, so um, I need to find a function which is not symmetric, but then which is
monotone.
monotonic.
Hmm.
So I need some function wherein if the values are same, so the values differ,
Hmm.
but the difference should be so XOR one per here.
Hmm. Okay, so just like think of additively constructing the truth table. Okay, so let's say I'm arbitrarily just choosing that whenever it is all zeros, I want my function to output a zero. Okay, now for the other thing, like let's say arbitrarily you choose whether you want a zero or one.
Yes.
Uh, so let's say you want a 1, let's say. Now what I want to do is I want to violate the symmetric property. So what should we do here?
So I mean violate which property? The symmetric
The
property.
symmetric property. So the symmetric property says that this block should always get a 1.
Right.
Oh, sorry,
Right.
did I draw it incorrectly? Okay, sorry, let me redraw this thing. Um, so I'll just shift this thing, okay? 1 0. I'll bring the 100 block here so that this block has a sum of 1, and I'll bring the 011 down here. And just rearranging so that uh, the sum here is the same. Okay, so by symmetric property this should also be a 1 and this should also be a 1, but I want to violate that here. So then what should I do?
And you want to violate where? I mean,
Let's say I want to violate in the next step.
oh, I see. So, I mean, I need to include a one here, but so I can include this. I convert 10 into a one. I mean, in this block,
Hmm.
I convert for this entire block. If you want to convert the symmetric properties, so then the number of the ones should differ in this block. So then I randomly flip any of the zero as one in this block.
Mm,
Or do you want something else?
uh, what do you mean by flip? Like, do you mean flipping here or?
Or anywhere, say anywhere. Like in the first row, you convert the very first zero corresponding to the literal say x1 as a one. Uh, one would mean that the Hamming distance of the second binary string,
Hmm.
which is a 001 now,
Hmm.
will get converted into a one. Okay, you can convert three. Okay, you can change. You can flip this also. So
Hmm.
then this will become 110, and then this entire block would become disbalanced. I mean, would become disbalanced in the sense that now we do not have the value of the Hamming distance is equal to 1 for all the three strings of this block.
Um.
So the question is that we are looking for a function and which is not symmetric, and which is a monotonic function. So therefore, you came up with this table and having 8 different possibilities. And in this block, the Hamming distance is 1. So I mean, within this block, the function is symmetric, but we are not sure whether this function is monotonic or not unless we write here the function values. So if I write the
Okay,
function
okay.
values,
So,
then
okay.
yeah,
Just one more thing there. So, you are right. So, in this block, if the function were symmetric, then all these three values should have been the same.
should have been the same because but yes, should have been the same
Should
because we
have.
have alternating values here. No other option, right?
Hmm. But this is, I want to construct a function which is not symmetric. So then what I will do is I will violate the property, let's say at this point. Because this part is fixed, because it's a truth table and it gives me all possible inputs that there can be. So I'm not changing anything here. The only thing that we want to change is in this table, in this column, right?
Right. Yes.
So if I want this to violate symmetry property, I'll, let's say, violate here. That means the sum of variables here is 1, and the sum of variables here also is 1, but my function is outputting different values.
Yes.
Okay, so this part is taken care of, that the function is not symmetric, but we want to make sure like that the function is monotone, that is, extend the values such that the monotonicity property is not violated at any point.
Uh, but the monotone property is being violated even I mean within this block also. Like say if you see the second bit, so this is a 0 and then I have
This
a
one
1
and this
here.
one.
Yes.
Okay, but if I call this, let's say this is x and this is x prime, is x less than equal to x prime in that order? Because for this, for every I in 1, 2, 3, xi should be less than equal to xi prime. But here this is not the case, right? So these are incomparable.
Right.
So it doesn't matter. Like if it's incomparable, we will not even talk about the comparison of their values. Only when this is satisfied, we will impose the condition.
Oh,
Okay. So then let's say here I write a 1. Even now nothing is violated because any two strings here are incomparable.
yes.
Now we want to be careful in the rest of the four parts and make sure that whenever this is greater than equal to any of the previous strings in this order, we shouldn't go flip from 1 to 0. Hmm.
So in that case, we should keep on maintaining the monotonicity from the left to the right. I mean, like say, I focus on the leftmost. I mean, this LSB, least significant bit, and start moving towards the MSBs. And then let us keep on comparing the LSBs with the LSBs of the other strings. And if we find inconsistency somewhere, then we are not bothered about the value of the function.
Hmm.
Otherwise, the monotonicity should be
Hmm.
maintained.
Right. Or the easiest way would be in this case that just make everything 1.
So if I make yes, that is also fine.
Because yeah, I mean, it's okay if you go from a 0 to 1, that is fine, but from a 1 to 0 you shouldn't go. So that the easiest way would be just make everything else 1.
Yes.
Okay. So okay, so then, although there's no name that we have for this function, but it's an explicit function which is not symmetric but monotone. And similarly we can think of functions that are neither symmetric nor monotone. Okay. So okay. Yeah, so this is the second part where we will need the induction. So okay, I mean, we may or may not need, but I think I'll skip this one for now. But this is the continuation of the question that we did. So we said that we saw this uh, definition of symmetric function, that f of x1 to xn is equal to f of pi of x1 pi of xn. For every permutation it's the same value, and equivalently we know that f of x1 to xn can be thought of as a function of the summation of the variables. Now we want to show that f can be computed by a function of uh, by a circuit of size n log n. This is where we'll really use this g. Okay, so show that g can be computed by a circuit of size n log n. And that would be enough. So what is a uh, I mean, what could be the ideas? How do we implement this G?
So if we try to implement this G through a circuitry, so we would be so we can keep the value of the fan-in is equal to 2 at a time. And why to keep the value this, I mean, 2 at a time?
Hmm.
We can keep all the n values, and so we can keep the value of the fan-in is equal to n.
Hmm.
So if and
Yeah.
then this will result into, then we find the sum of
Hmm.
this thing.
This boils down to hmm. This boils
Yes.
down to how do we find the sum of n. So you have x1, x2, so on up to xn. All you want to do is you want to find the sum of all these bits, but this is an algebraic sum, and you want to implement this only using and or negation gates.
Yes.
Yes. So this is basically saying how do we add n 1-bit numbers. That is what we want to implement. So this is same as adding n 1-bit numbers.
So
Okay.
what we can do is that we can go for this parallelization kind of a thing, and we keep on adding two
2
numbers
2.
at a time,
Exactly.
and keep on moving up in the hierarchy, and that would require the log n number of the heights, and then number of labels, probably there would be n or how many labels. So
Hmm.
multiply by that. Yeah.
Yeah. So yeah, but at each point we could potentially have increased the number of bits, because let's say how do we add two 1-bit numbers. So um, if it's um, both are 0, the sum is 0. Either of them is 1, then the sum is 1. But uh, this is the tricky part, where if both are 1, the sum is 2.
Yes.
Yeah. So
Then the sum is equal to 2. So if we have both the ones, uh, so how to know that? I mean, whether both the values have become equal to 1.
hmm. So then what we will do is, what do we do in how do we add two n-bit numbers in binary? Let's say we'll write a 0 here, carry forward the 1, and write it here.
Yeah.
This is 2 in binary. So we'll do the same thing. We will introduce one more variable which says the carry forward. In this case the carries are zeros. In this case carry is 1, and the um, least significant bit, let's say that bit is 0. Okay, so that means you will get 2 bits here after you sum up.
Yes.
So how is that done? So the carry is basically an AND function, right? So this is an AND of x1 and x2, that is the carry bit for us, and this is a parity bit.
Yes.
So
And how are we implementing this carry bit here?
this is basically AND of x1 and x2, right?
Yes. Right. Yeah.
So this is parity. I'll just write it as parity. We know that parity can be written as in terms of AND or negation. So this is our first bit, and like you said, we'll do the parallelization. So I'll call this C1 B1. This is the first carry bit, second carry bit. This is C2 B2, and so on. Okay. Now we want to add these two at a time. So we are adding two 2-bit numbers. We are adding C1 B1 with C2 B2.
Uh, so, like if I add 0 1 with 0 1. So if I add 0 1 with 0 1, then I should get the algebraic sum. So I should get the value as, what should I get? 0 1 and then 0 1. So should get the value as 2. Algebraically, I should get the value as 2, and but in this case, I will get this value as 31. So do that. So
So, um, so this part is same as this part. This can be implemented by parity. This bit is parity, um, because uh, if both are 1, this bit is 0.
yes.
Okay, then there may be one more carry forward. If this is 1 1, then this bit is 0, but there should be a carry forward here. Okay, so then there will be one more carry here, and we need to add these three now. Okay,
So this way, I mean, let me keep on, doing this.
parity.
Yeah, okay.
Exactly. So you are basically doing parities and carrying forward the new value and doing parity again. That is correct. So this is repeated ANDs and parity. Okay. So yeah, so you are right. So the depth of this is log n, and then we need to show that at every point the number of gates that we ended up using was uh, yeah, order n or something. So at every point, if you are order n, then altogether we would have used order n log n gates.
Yes.
Okay. So okay. So I'll leave out the details of this maybe for now, but yeah, the idea is clear, no?
Yes, idea is clear. Yeah.
Okay. Okay. So how many questions? Okay. So I'll define this class now, which is called p/poly. So this is called p/poly, and how is this defined? So we say that a language is in p/poly if there is a deterministic Turing machine M that takes, okay, I'll call it deterministic polytime Turing machine because this P tells you that it's a polytime machine, Turing machine M, and there is some advice function that I'll call h. H is the advice function. Okay, it takes as um, okay, so it takes as input n, where n is the length of the input for us. Okay, so what that means is, for every x in the language which is of length n, h is going to give me the same string. So it does not depend on that particular input, but only on the size of that input. So this is not exactly like the symmetric function, but it's somehow behaving like a symmetric function, where it does not depend on the value of what the exact x1 to xn were, but just the length of it. Okay, and then using this advice function, uh, yeah, that uh, such that I'll just rename this to b, such that whenever x is in the language, b of x comma h of x will say 1. Okay, so how is this different from p? When we have p, we basically don't have this advice function at all. We don't have this extra h of x here. We just have a decider b. Whenever x is in the language, b of x is 1. But now we have this extra advice, which is the same for the same input lengths. So for all inputs of length n, the advice is the same, h of x. So I should call it h of length of x actually, because it does not depend on x, but only on the length of x. Okay, and using this advice, the decider b is able to tell whether to accept the string or not correctly. Okay, so this poly tells you that what this h of length of x, so what is h of length of x? It's a string here in 01 star. Okay, now we don't want this to be any arbitrarily large string, because if it's arbitrarily large, then I could as well tell whatever, I mean, then everything would be decidable, because I can just give you the answers, or as long computation you need, or all the sets of configuration through which it goes. So this could contain arbitrarily large amount of information. To restrict that, we are going to put a restriction that the length of this should be bounded by polynomial in the length of x. So this is not an arbitrarily large advice we are giving, rather it's a polynomial sized advice, which is why we have a poly here. So we can think of other extensions of this.
I have a question at this point. So how this advice differ from a certificate? Like say I can easily I'm thinking of modeling this capital P as a verifier, say V.
Right. So okay. So notice that in case of the non-deterministic machine, for example, um, you could have different uh, certificates for different inputs.
Yes.
Even though the length of the inputs is same, the certificates could be different. For example, think of uh, two Boolean formulas of the same length. Okay,
Yes.
but there
Yes.
could be different certificates for each of them.
Right. And here the advice string is going to remain the same for what?
For all the inputs of the same length.
Uh, Same length. All the inputs of the same length. But considering that this computation is non-uniform, so we don't want to generalize anything. And here, but then here we are generalizing things over the length of the string x or what?
Uh,
That for
Generalizing
all
in
the
this,
strings.
Generalizing in the sense.
Generalizing in the sense, like say in the uniform computation, we design a single Turing machine and that works for all the inputs.
Hmm.
Like the people used to say that an algorithm is the finite answer of the infinite problems,
Hmm.
right?
Hmm.
So in that sense, say since the circuit complexity, the things are non-uniform, and we design a circuitry specific to a problem instance.
Hmm.
So here, how is that possible that we are using the same advice?
Hmm.
I mean, for multiple number of the problem instances. Is it like this that we are using the same advice for the multiple instances of the problem having the same size?
Yes, yes. For
Oh,
all the instances of problem that have the same size, we are using the same advice function.
oh, okay, okay, yes, now I understood. Yeah, thanks.
Okay. Oh, so we didn't also talk about circuits as of now. The entire definition only concerns the Turing machines as a model.
Yes, yes. And I have one more question that I heard the term alternating to machines, ATM.
Hmm.
So I vaguely remember that probably those were the Turing machines wherein this facility of advice used to be available.
Hmm.
So I mean, are we talking about the same ATM here, or something else?
Um, okay, so I don't exactly remember the exact definition of ATM.
Okay.
Mm,
All
okay,
right. Yeah.
but okay, maybe at the end I'll check this. I'll check this out and we
Sure.
can
Sure.
talk.
Sure. Sure.
Okay, okay, good. So okay, so now we have this p slash poly class. Okay, and you can think of like you can ask, okay, why is this Turing machine a deterministic polytime Turing machine? I could call it a BPL machine, or I could call it an L machine. It could be any complexity class. Similarly, you can say that, okay, why should the uh, length of this advice string be restricted by polynomial in terms of the input length? I could put some other restriction. I could allow it to be a constant size, maybe just two, or maybe yeah, maybe allow it to be log n to the log n or something like this. So basically there is an infinite set of possibilities here, where instead of p you can think of some other complexity class, and instead of poly you can think of some other length for the advice string, and you will get a new class. But we'll be interested in particularly in p slash poly, because it has this nice characterization that p slash poly is same as p size, which is the set of all poly size circuits. And the proof of this is also not hard. At least one direction would be easy. So for example, let's do yeah, okay, let's do the reverse direction, that p size is contained in p slash poly.
So I could not understand this new complexity class P size.
Okay, so uh, okay, so we know that not all functions have poly size circuits.
Does not all. Is it because of that counting
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 argument,
Okay,
yes.
all right, yeah, fine.
Right. So yeah, so this is the class of functions that which have a polynomial sized circuit with and or negation, the standard gates, the standard basis. mm, yeah.
But then this used to be the definition of this used to be the definition uh, with little tweak here and there. This used to be the definition of AC and AC and NC as well. Because
So
in the AC also we do have a polynomial size circuitry. If we forget about the panel limits, and then the same works with NC also. And moreover, the same is for the PY poly also, wherein we are restricted to have the circuitry of the depth of the polynomial depth only. So why this new complexity class in P size?
Okay, so you're talking about AC, NC, and what is the other class that?
PY poly itself, PY poly itself. That
Huh,
also
but
says
this,
that also says that it is a collection of all the circuitries of the polynomial size.
hmm. So this is something that we want to prove. Okay, but as of now, by definition itself, this is a definition with respect to Turing machines.
Because uh, even in the notes also they give the definition as in the form of the circuits only. That this PY poly is the collection of all
Okay,
the circuits
okay,
and which have got the polynomial size.
okay. So did we do this definition in the class?
Yes, I saw notes, so they are given two definitions.
Hmm.
One is in the context of the circuits,
Right, right.
and other is
And
in
the
the
other
context
is
of Turing
that there
machine.
is a collection of all polysize circuit,
Yes, yes,
which
yes.
is the class called p size. So okay, so the way it happened is that on one side you have a definition with respect to Turing machines. Okay. On the other hand, we have all these classes that we studied, right? The AC, NC, and so on. Among those, we were always interested in circuits of polynomial size, which we call p size, and it so happened that they are equivalent.
Oh, yes, now I understood. Yeah,
Okay.
and
And
we wanted to prove this.
huh. And how
Yes.
is this different from AC and NC? So notice that the way we defined it always with respect to the depth. So this is union of NCI, where I is greater than equal to 0, where that NCI basically means that the depth is log n to the I.
Yes.
Hmm. And in that process, because the depth is uh, let's say log n to the I, and we know that gates are of bounded Fanon and so on, we can do calculations and find out the size of the circuit. Okay, and it could be that these are polynomial size, but it may not be that all the poly size circuits are covered by this.
So does this mean that in the case of the NP, the depth is log of I of n. So if depth is of the order of log of I of n,
Hmm.
then what will be the size? So 2 raised to the power the log of I of n, and 2 raised to the power log of I of n value
Hmm.
came up to what? N raised to the power I, and so we would be having polynomial size circuitry. So what is left? I mean, yeah,
Agreed.
beyond
So
this.
what if there is a polynomial size circuit with polynomially large depth? That will not be covered by NC, because NC only covers the powers of log.
Uh, yeah, so that possibility is excluded in C, wherein we have height, polynomial height, and moreover the number of nodes are also polynomial. Can this happen? Can this happen? And when can this happen? So we have maybe it could be the case. Yes, polynomial height and then polynomial number of the nodes, quite possible. Yeah. So those are going to be covered in this P side.
Precise, exactly,
Okay.
yes.
Yes. Yes. I understood. Yeah. Thanks.
Okay, good. So, hmm. Okay, so to see this, okay, did we also do the proof of this in the class?
No, in fact, I saw notes, but in the notes, this p-size class was not given. P by poly was given, and then
Okay.
one Karp-Lipton theorem was given, and which states something, some relation in between NP and then P by poly,
Hmm.
and which says that if it can be established, then the hierarchy will get collapsed at the level of the program. That was given.
Right, right. Okay, okay, okay. Thanks. So, hmm. Okay, so basically the name was not used, but the direct equivalent definition was given. Okay. So, okay. Um, hmm. But okay, now that we know that the two definitions, so this is the set of all functions that have polynomial size circuit, and let's say you want to show that P is contained in P size is contained in P slash poly.
Yes, so if we need to show that the group, well, right, yes. So if P size is given, so we have been given a circuitry of the polynomial size. And if we have been given a circuitry of the polynomial size, so
Also,
this entire circuitry can act as an advice kind of the thing that okay, uh, maybe say that sort of thing.
Hmm. So yeah, that is correct. So notice that when we know that circuits are non-uniform model of computation, so we need um, a family of circuits. Right, so when the input length is 1, there will be one particular circuit dealing with all inputs of length 1. When input length is 3, there's a particular circuit dealing with it. So we had a family of circuits.
Yes.
Yes, and you are right. So for all x in the language, whenever the length of x is n, what the advice function will actually do is it will tell you the description of the circuit. Which circuit should you use? So h is actually going to map this. Okay, I'll just call it x for now. So h of x is basically going to give us the circuit, the description of circuit, um, corresponding to the length of the input.
Right, and this would be similar to the scenario where in the examination I gave the cheat sheet as well to so this cheat sheet would be similar to the advice that yes. Right,
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 right.
right.
So now that we have this circuit, all that we are going to do is we have this circuit, so we are going to run our input x on this circuit, find out the value that it computes and output that.
Yes.
And because the circuit is polynomial sized, this is something we know, the entire computation can also be done in polynomial time.
Yes.
Therefore, we are doing this in in polynomial time, given the advice.
And this can happen in both the directions. I mean, can we use the same argument for this P by poly can be is a subset of the P size? Because then whatever advice we are having, so corresponding to that advice again.
There will be a circuit.
Yes.
Yes. Hmm.
So
Yeah.
where does this MP thing I mean fits here? Because if P is the subset of the P by poly P complexity class, because if I do not use any advice at all, whatever advice Turing machine is giving to me, I just keep on ignoring it. So then this P by poly probably would be seen as P. But then where is that issue with this NP thing so that this Karp-Lipton theorem, the separate theorem altogether came into the picture? That we are not that much sure of this NP stuff and this P by poly.
Okay. So So just to draw what you said, so we know that P is contained in P slash poly, because just don't use the advice, and you'll still be running in polynomial time. So P is trivially contained in P slash poly. But the carp, uh, what was the other name?
Karp-Lipton, Karp-Lipton.
Carp-Lipton, yes. So what they show is that PPP is contained in P slash poly. We know that P is contained in BPP by definition. Okay, so you are asking where does NP stand here?
Yes.
Okay, so yeah, so again, like um, yeah, you might recall that this status is an open,
Yes,
like
it's still unknown.
we don't know anything, any side of containment,
Yes.
or yeah, so yeah, we don't know any of that, and also we don't know whether this is true, because particularly because of um, I think it's because semantically what's happening is like we said earlier, that for two different inputs of the same size, the certificates could be very different. So we don't know yet how to combine, uh, how to sort of capture that by just one function.
Right. And even I could not understand why this BPP is contained there in P by poly.
So yeah, so mm, yeah, I don't have the proof fresh in my mind, the Carp-Lipton proof. Um,
So what is this this car Lipton is this related to the NP and the P by poly, or is this related to the BPP and
PPP and
NP?
the P slash poly, yes.
Oh, I see,
So
I see. Okay.
yeah, so
Okay.
yeah.
So I mean, in order to connect the classes which are related to time and the classes which are related to complexity, I mean, people used to consider which points, like say, like you said, that for the string of the same length, the different properties are possible, but then the advice would remain the same. So I mean to say that how is that possible that we are going to connect the complexity classes of the two different domains? Like say here you connect this BPP and with P and PY poly is trivial. And so how is that possible that circuit complexity classes and the time complexity classes are going to be connected somewhere?
Mm, you mean other than the fact that here we have one uh, class in terms of circuits and the other in terms of
Yes,
Turing machines. Other than
yes.
that, how do we
Are
connect?
they, yes, yes. How do we connect? So, like, say, connection would mean that we are trying to connect something specific to something general. Because, I mean, all the complexity classes which were there in the time domain were general. We were defining a single complexity class for all input sizes, and here we are specific to the input size. So, how is this happening that
Um,
circuit complexity is going to be connected to the time complexity, number one, and
o-
second,
okay,
yeah,
okay.
and
Okay, to answer that, so the P slash poly is not restricted to the input size as such, because the input to that to a language in P slash poly could be anything.
yes,
Hmm.
yes, because P is also there in P by polynomials, right, right.
Hmm. Okay,
But yeah, but then it was also given that even the undecidable problems are the part of the P by poly. The problems which are undecidable are also contained, are also there in P by poly.
yes.
So how is that? I mean, why to
So
like say the halting problem. So halting is also there in P by poly.
hmm.
How is that? I mean,
So are you asking why it is?
yes, yes.
Okay, okay, okay.
Why?
Good. Okay, okay, okay. So okay. So we know that surprisingly there are undecidable languages in P by poly. In fact, something strong, very much stronger is true. It's contained in P by 1, that you don't need polynomial advice, you only need one bit of advice. So, how do we see that? So, let's say you have the halting problem. We know that halting problem, or HP, is undecidable. This is a fact that we will use for now. We will not prove this. So, what is HP? HP says the set of all mx, m halts on x. So, it is the set of all machines, comma inputs, where the machine on that particular input halts. It may accept or reject, but it doesn't loop. Okay,
Yes.
so we know that this problem is undecidable. Now, whenever we talk about the input, we always talk about a binary encoding of it.
Yes, encoding of the input as well as
Encoding of,
encoding of the deviation.
right. So think of m comma x as input to the HP. So there is some binary, there is a binary encoding with, therefore the input to HP is going to be a binary string. Okay, but the interesting thing that happens is that you can actually think of this as a unary input. So let me call this UHP, or the unary halting problem. Okay, and the problem is same, m comma x, such that m halts on x, but the the encodings of mx, they are all unary. So this is basically a string of the form 1 to the n.
And how is that possible?
Exactly. So how is that possible? So think of, suppose I could show you a bijection sigma which takes a binary string here and maps it to a unary string here. Okay, and furthermore, it's a bijection. Okay, then what I could do is that whatever encoding you're giving me as a binary string, I will use this sigma, convert it into a unary string. Okay, so for example, I'll take my halting problem and I'll look at all possibilities, all possible mx's here, and I'm going to use my sigma here, convert this into a unary instance of mx, and do that for all of them. Okay, and because it's a bijection, it will look like this. So every instance here will have a unique unary mapping, right?
Yeah, I lost. I mean, this flows somewhere at this point
Hmm.
that wherein we define this bijection.
Hmm.
So I could not understand that how are we defining this bijection in the sense that I have a pretty large binary string,
Hmm.
and so probably and we are enumerating the entire binary string
Hmm.
to a one
Hmm.
star, one
Hmm.
star,
Hmm.
one star.
Yeah.
Something similar to diagonalization or something. No, different
Hmm.
from that.
It's
So
different.
for
Yeah.
so for one for every binary string,
Hmm.
we can find
A unique
a
unary.
unique one. No, but then tell me, say if the length of the binary string is same,
Hmm.
so in that case, how would we have such an encoding wherein I mean, what could be the way?
Hmm. So, okay, I'll tell you I'll define you exactly, explicitly what this sigma is. So, you're right. So, on this side, it looks like this set is very large because you're allowed two alphabets here, and here it looks like this is potentially smaller. So, it looks like there may be many options here, but maybe there is nothing to map here. Okay. But notice that we're dealing over infinite sets. So I just want to prove you that there will always be some mapping here. So let me come back to this and let me define this bijection explicitly. So let's say my bijection function is very simple. What it does is, input to it is a binary string in 0 1 star. So let's say it is 101 100 something. Okay, and what I'm going to do is I'm going to find its decimal value. Let's say its decimal value is let's say 1042. This is the decimal value of that string. Now I can write this as 1 to the 1042.
Yes, that's
Okay, there's only one small catch here, that okay, this um, okay, I'll not write this. Okay, so this string and this string. As binary strings, they are different. Everything here is same, only that there's a 0 here. As binary strings, they are different, right?
So yes.
But as decimal value, they will be the same.
So yeah.
So then, how do we get around that? So what we'll do is we will additionally pad a 1 to it. So you give me a string x, which is a binary string. I will look at 1x, just 1 concatenated with x. Now this makes sure that two strings of this form are treated differently.
Yes.
Yes, and now we will look at the decimal value of this and write 1 to that decimal value n.
Yes, and possibly divided by two. Yeah, I mean, so we are writing this as so the decimal equivalent of 1x is say n. So in the unary, it will get represented as 1 raised to the power n. I mean n number of the one. However, since we have appended added a 1 towards the left, so the value of x has been changed, isn't it? But it's okay. It's okay. The representation is fine. Yeah.
Yeah, exactly. So we now know that there is a bijection from binary strings to unary strings. So then what I'll do is we will just encode this in in unary.
Yes.
So by using our sigma. Okay, so now we have this new problem, which is a unary. We have a language UHP, which is a subset of one star, and UHP is also undecidable, because if UHP were decidable, what I could do is I could use this sigma, come back to its binary value. I mean, so this is basically a reduction that HP reduces to UHP. Because, so can you think of this?
Uh, yes. So yes, this is okay. HP can be reduced to UHP. Yeah.
Yeah. Okay. So yeah, so we know that this is also undecidable. Now what we'll do is think of um, okay, so we want to show that UHP is in P slash poly. That would mean that there's an undecidable language in P slash poly.
Yes.
Okay, so what is the advice that we would give? It's not even poly, it's only one bit advice that you need to give.
So then, since UHP has been encoded into a number of the ones, so then I need to check that whether the Turing machine is getting halt over the input X or not.
Exactly.
So, and I need to give a fruitful advice so that I mean we should be able to decide or decide or what.
Decide
So,
whether to accept or not. Yeah.
yes. So, what would advice be?
So,
Now
okay.
I'm unable to think. Yeah.
So you're almost there. So basically, that advice is your input is x. Input to the language is x, which is a string in. Okay, and what we'll do is the advice function basically uh, says that look at the length of x, and if the UHP, uh, so if okay, is 1, if 1 to the length of x, or yeah, okay, is in UHP and 0 otherwise. So it's basically telling us the membership of that string in UHP.
But then that itself is the uh,
That itself is the input itself is the length, because this is happening because we only have one alphabet. So there cannot be two inputs of the same length.
yes, but still somehow I missed something. I could not understand this thing, that why the form of the advice is like this and why this advice is going to work. So what we have done so far is that we have encoded an instance of the halting problem HT into an instance of the UHP, and which comprises of only the ones.
Hmm.
But still the problem remains the same, that whether the given Turing machine is going to halt for the given input or not. So now, what kind of the advice? I'm getting that too by just by through one bit. What kind of advice is this?
Hmm. So, okay. So the advice is just that if that input is in the language of UHP, it tells you to accept. If it is not, it tells you to reject. Why is this working? Because why does this not work if this were like a 0 1 star? Because there could be different inputs of same length.
Uh, but determining whether this one is, this is such a very trivial advice. Must be going to the solver of the problem as well. Like say, if one raised to the power x is an element of the UHP.
Hmm.
Now this, moreover, this one raised to the power x is the element of the UHP means what? This is just the encoding of the problem instance.
This is it, you can think of it as x itself. You don't even, yeah. So just think of this as x. So okay, why is this working? Because we never said that h. Um, we are talking about h, the existence of h.
It's okay, but my actual problem is that UHP is still the nature of the problem remains the same. Only the encoding has been changed by using a bijection.
Hmm.
And the problem is still the same, that we need to decide that whether for the given Turing machine and the given string, the Turing machine halts or not.
Hmm.
The entire thing has been converted into a sequence of the ones. And
Hmm.
now the advice which I am getting is that, okay, you say that this Turing machine halts for the string x if you find that the number of ones in the description is an element of the UHP.
Hmm.
So this thing I know this thing,
Hmm.
that if this string, if whatever I am getting belongs to a UHP, so what is the probably I'm missing something, but what's the meaning of this advice? I'm unable to understand that. Is there any relevance of such a advice?
So if the advice were not there, then you wouldn't be able to. I mean, if you just remove this advice thing, then we won't be able to decide
Uh,
um, whether it's in the language or not.
why? Because even if the advice is not there, I would just be having a sequence of the words. That's it.
You will be having a sequence of ones, but that is undecidable.
That is
So that is
undecidable.
undecidable. So how does a deterministic Turing machine? So I mean, by definition, you cannot come up with with a Turing machine itself. Forget about poly time. We just cannot come up with a Turing machine.
So does this mean that now this entire sequence of the ones is placed over a a different Turing machine, the deterministic Turing machine, and its entire content is placed over the tape of the Turing machine. And now I give an advice to the newly constructed Turing machine, and which is
Hmm.
holding an instance of the USB over the tape. That okay, the Turing machine you display one.
Hmm.
If you think that whatever string I have placed there over the tape is an element of the USB. But
Exactly.
then the deterministic Turing machine knows with the surety that yes, this indeed is an example, is an instance of the UHP only.
Because it has the advice.
Uh,
If the advice were not there, then we couldn't even have come up with a Turing machine.
Right, but then now the question is that if I place any sequence of the ones there over the tape, that is going to be an instance of a UHP. So can you tell me a string of the ones and this is not an encoding of a valid UHP?
Mm, no, I didn't understand your question.
So if I write say 1,000 times once over the tape of a newly constructed deterministic Turing machine,
Hmm.
and I give that Turing machine and advise this that okay, you please display one. If you feel that I have placed 1,000 number of the ones, if this is an instance of the UHP or not. So now the Turing
Oh,
machine, the
okay.
deterministic Turing machine will say that I do not know what this. Whether this is an instance of the USP or not. Quite possible that I can
Uh,
always model this 1,000 number of the ones as an instance of a UHP. Some portion to decode the functioning of the Turing machine, and some portion for the input.
okay, okay. I just want to make sure that I understood the question. So, what you're saying is that on the you're imagining the advice as written on the tape.
Advice is not written over the tape.
Hmm.
Over the tape, an instance of the USB is written
Okay, which
because
is an input to your okay. Mm-hmm.
yes.
Okay, but the question is whether it belongs to the UHP. You're basically testing the membership, whether that.
Yes. So, but then the Turing machine, DTM, has got a very, very limited capacity. So, how such a Turing machine is going to decide that that I have written 1,000 number of the ones there over the tape, that whether this is a valid instance of a UHP or not? Because the Turing
Um,
machine will always say that okay, if I give you say one million number of the ones
hmm,
in an encoding,
hmm.
then I can always view it as a valid instance of the UHP because then I will break
What is
that
a
1
valid
million number of
instance
the
for?
ones.
What is a valid instance for you? The one that belongs to the language, or
So because the language itself, so this UHP is what this UHP is a sequence of the words that is, and some portion of it would be the description of the Turing machine, and some portion of this would be the given input, isn't it?
uh, are you sort of thinking of this and this as different parts, or
No,
huh?
because in this entire encoding,
This in
since the entire encoding has now been converted into
into
a sequence of the ones using
ones.
that bijection. So now my point is that even if you write, write here, say 100 ones.
Hmm.
So can't I consider this 100 ones as an instance of a
Hmm.
UHP? Right? Because quite possible that 80 ones would be representing the description of some Turing machine,
True. True.
and the 20 number of the ones would be representing say some input.
True. Yeah.
So whichever string I write here over the tape would
Is going to
definitely
be
be
some.
an
Yeah.
yes
Yeah.
instance of the
Yeah.
UHP language. So, I mean, the problem is still remains the same. The only thing is that we have added another layer of the decision making. That instead of, in fact, this is probably there in the formulation of the halting problem itself. That can we design a Turing machine, and which will take another Turing machine and an input as an input and tells me the finite amount of a time
Hmm.
whether the inputted Turing machine is going to terminate or not.
Hmm. Hmm.
And now we have added only one thing, a small piece of the advice
Hmm.
in this definition of the HP.
Hmm.
So my point here is that still the problem remains the same, and there is no impact of adding this advice. That okay, you display one if whenever you feel that X is the element of the USB. This is the very nature of the Turing
So
machine. It is going to display one only if the membership holds true.
yeah, but is there a machine that will decide? So no matter what, I mean, the input that you give me are some ones, 1 to the n, whatever that n may be, and you want to decide whether it is in UHP or not. Now, um, the point is that um, the point is that because I don't know how. Because it's undecidable, you don't really have any machine that will be able to correspond to that language.
Right. So while proving that
Hmm.
while proving that the verdict problem is undecidable,
Hmm.
we prove it by the contradiction kind of a thing, and
Hmm.
then we used to show that the construction of such a Turing machine is not
Right.
possible.
Some diagonalization argument. Yeah.
Yes, yes. So that is not possible. And if the construction of such a Turing machine is not possible, then the number one is construction of the Turing machine is not possible because somewhere that it's quite possible that we would be taking the Turing machine itself as an input
Hmm.
to decide,
Hmm.
and then the things won't be possible.
Hmm.
It's okay. It's okay. So now that we are using an advice also, so the first point is that we are assuming that such a Turing machine exists.
Hmm.
And the second thing is that if I give just one bit of the advice, then the
Hmm.
Turing machine would be able to decide. And the advice given is very trivial.
Hmm.
That whenever the Turing machine feels that this string is the element of the UHP, then displays one, otherwise zero.
Hmm.
So that is slightly beyond understanding. Yeah.
Yeah, yeah, this part is, yeah, because it doesn't seem like this one bit of advice could actually be so powerful. That's the.
Not only
Huh,
powerful,
huh.
but then how can we claim that the problem is undecidable and still, beyond the fact, we are assuming that okay, such a Turing machine exists,
Hmm.
and this Turing machine will work in the presence of this very trivial advice.
Hmm.
So who is that person? The problem
This.
is undecidable. The problem is undecidable. UHB is undecidable.
Hmm.
So no Turing
So,
machine exists.
okay. So what you are not convinced of, is how is this one bit of advice really making it decidable?
One bit of the advice. So this one bit of the advice is not going to make
Make it
anything decidable because
true.
there is no one to take advice.
Because there's no one to take advices.
Advice, yes, because in order to take the advice,
Hmm.
there should exist there should at least exist a Turing machine. And now since the problem itself is undecidable,
Hmm.
the halting problem is undecidable, so there does not exist any Turing machine
Hmm.
which can show the membership.
So we are not saying that this h, so this would be decidable if this h were decidable by a Turing machine, but that is not what we are claiming. Where h is just a function, right? So as um, I mean, h is basically just a function from.
Uh, uh, I, I could not hear this. What did you
Sorry.
say?
Huh. So.
H.
Uh,
Okay, you wrote things here. Fine. So H is a function from the this one, the cleaning closure of
hmm.
one to 0, 1.
Hmm.
It's
So.
it's okay. It will take a sequence of the ones and then it will produce either 0 or 1.
Hmm.
Uh, yes.
Hmm.
But then, so this H itself is a Turing machine then, because that is the job of the Turing machine. The cleaning closure of one is placed there over the tape of the Turing machine, and the Turing machine is going to decide whether this particular sequence of the ones, belongs to a particular class or not.
Mm, hmm. I get your point. So I think you are saying from this function we could go to the Turing machine.
So I need to say that this is the last thing which we require actually. That I place the sequence of the ones over the tape, and someone tells me that whether this is a 0 or 1, and that would be the job of a decider, and that the Turing
Uh,
machine shall decide.
yeah, but we never claimed that we will give a machine.
So
So
if there does not exist a machine, that who is going to take the advice then? Because in order to take the
no,
advice, there should exist a Turing machine.
we didn't say that there's a machine for H, is what I'm saying. The machine only takes the advice H. We don't know how, whether H is computable or what. That is something we don't know. But suppose there is such an H which is given by a function, then the problem, yeah.
Oh, I see, I see. Now I could understand something. So this is something like Oracle thing, Oracle stuff, some sort of.
Sort of, yeah.
Yes. So if that is the case, then it's fine. Then miraculously, then somehow someone is giving me advice.
Hmm. Hmm.
Okay.
Hmm.
Yes. So probably there could be some relation then in between this circuit complex, this P by poly, and
Hmm.
the Oracle complexity classes as well. Might be. Yes. Because this giving this advice, if it is somewhere equivalent to having an Oracle, then it's fine. Probably
Hmm.
then, is this true that through the OTM, through the Oracle Turing machine, then we
Hmm.
can address the undecidable problems as well?
Through
No,
the
not sure. Through oracles can be addressed to the undecidable problems also.
um, yeah, so in the semi decidable, so I think throughout the course we were looking into the decidable world where npp everything was decidable. We knew there is a Turing machine. Similarly, if we go to the computability world, we have a hierarchy of, so similar to the arithmetic hierarchy that we saw, where similar to this hierarchy where we have NP, the class of languages that become decidable if you give access to SAT, or this is same as NP to the NP. Then we have this whole, this is our sigma 1, sigma 2, and so on. We had this hierarchy. Similar to that, there is a hierarchy in the computability world, which is, let's say, halting problem. Okay, this is the semi decidable language which is not decidable. Then we have HP to the HP. This is a class of languages that become semi decidable, that become decidable if you have Oracle access to HP. And this is called SD to the SD. And you can go on further, like this is an infinite hierarchy. This is also called sigma 2, this is called sigma 1, but this is polynomial hierarchy. uh, I mean, we have everything is done with respect to polynomial time. Here there's no time, we are just talking about whether it is computable, so there's no superscript here. And similar to the pi, the co np thing, we also have co st that will give us the pi's. So
Oh yes, yes, yeah. This thing is totally new and yeah, and this was not given in notes anywhere. Yeah, say that. Yes, this thing computability. Yes, yes. Okay, okay.
so this
Thanks.
is, sorry, I'm sorry, I think I rewrote, I mean wrongly labeled. This is the polynomial hierarchy, and
Yes.
this is the arithmetic hierarchy. This is called arithmetic hierarchy.
Okay, okay.
Okay.
Yeah, fine. Yeah, thanks.
Okay, good. um, okay, so I think there are some other questions here. Maybe we'll do that next time, or it's there in the PDF that I'm uploading, so you can even take a look at this. um,
Sure.
okay,
And
so
which topic shall be covered next time?
has the content been uploaded? So I think we'll do touch theorem, some randomized circuit complexity classes that should be coming up. So I mean, I don't know beforehand, like I'll get to know only when it's uploaded. So
Okay, okay,
hmm.
okay.
Okay, but next week we'll meet same time, Saturday, yeah, 10 a.m. to 12 p.m. Okay.
Sure. Thank you so
Thank you.
much.